When it comes to teaching your 4 operations, there seems to be this raging debate that doesn't seem to die between the older way of doing things, so doing your standard algorithms, versus more conceptual ways of understanding and breaking apart those problems. One of which is the area model of multiplication, sometimes called the box method. And so I'm going to weigh in on this debate and explain why I really like the box method and how I feel like this over the traditional algorithm helps students develop a more number sense, but also to get them to think about multiplication a little bit more flexibly. So just for a quick demonstration on how the box method actually works, I'm going to show you with this problem here, 8 times 15. So I'm thinking of this rectangle as having 8 15s. And so instead of just having to multiply it by 15, I can break that 15 up into a 10 and a 5. So I'm still thinking about this as having 8 15s here, but now I've split my 15s into 10s and 5s. So now I can just multiply 8 times 10 is 80, and 8 times 5 is 40, and then I'm going to add those together, which is going to get me to 120. Now, one thing to note here, you might have noticed that I've tried to keep these boxes proportionate. So for example, the 10 is twice as large as the 5 here. And so I feel like that's important to try and do, because the whole point of doing the box method is to conceptually emphasize what's happening. So I'm picturing my 8 rows of 15 within this area model. Well, if we just had, say for a different example, 15 times 22, if we just simplify it down and say, all right, every time you just draw a box, then you put your 10s at the top, your 1s down the bottom there, you put your 10s across the top, then your 1s, and then multiply across, you've kind of just stripped it back to a random process to follow. In that case, they might as well just stick with a normal algorithm. And so in order to avoid it becoming just a process they follow, I like to start by teaching the box method using concrete materials like these cubes here. So, for example, let's say we wanted to work out 5 times 12. Well, here, straight away you can see that I have my 5 12s. 1, 2, 3, 4, 5. But 5 12s is quite a bit to think about. So, instead, we can use the box method to break apart our 12 into more manageable parts. So, I'm going to keep my 5 on this side, but instead, I'm going to break my 12 into a 10 and a 2. So I'm going to split apart my area, and I'm going to split my 12 into 10 and a 2. So now we just have to work out the total of each section. So here now we can see that now I've got 5 10s. So 5 times 10 is 50. So I know that altogether there must be 50 blocks right there. But then we can also see here that I have 5 times 2. And so this must be 10. Clear why we need to add the 50 and the 10 together to get our total to the problem, because by adding 50 and 10 more 60, we know that there must be 60 blocks altogether. Now, you also don't even need to necessarily jump straight to 2-digit multiplication to introduce the box method, because you can even start on some smaller multiplication, single-digit sums, and particularly the ones that students get stuck on. So for example, here I've got 6 times 8. Now, I could choose to solve this in multiple different ways. For example, I could keep my 6 on the side again, but I could break my 8 into 2 4s, like this. Now, I'd work out 6 times 4. I could use my double doubles, so double 6 is 12, double 12 is 24, and then if that one was 24, this one's got to be 24 too, and then all together, I've got 4 10s, 40, and 2 4s, so I've got 48. But that's not the only way we could solve this. So for example, instead of breaking the 8 this time, let's say I wanted to break apart my 6. And let's say I'm good at my 5 times tables. So now, instead, this time I'm going to break my 6 into a 5 and a 1. So I've broken my 6 into 5 and a 1. And I'm going to keep my 8 here. And so 5 times 8 is 40, plus my another 8, 48 altogether. And now for a final example, let's say I had 7 times 11. Now, if I wanted to, I could break both these numbers apart. So I could split my 7 into a 5 and a 2. And I could split my 11 into a 10 and a 1. So now 5 10s is 50, 2 10s are 20, 1 times 5 is 5, and 1 times 2 is 2. So altogether I'll have 5, 6, 7, 10, 70, 75, and 2 more 77. And look, I know there's going to be some of you out there that are like, well, this is a ridiculous amount of steps for something like 7 times 11. Shouldn't they just know their 11 times tables and know instantly that that's 77? And yes, while I agree with you that yes, they should, it all comes down to what our actual goal is. And in this case, our goal is using some smaller numbers to demonstrate the distributive property and how it works, so that when they're presented with a problem beyond 12 times 12, they've got flexible mental ways to think about it. So that down the track, when they see a problem that's beyond the 12 times 12 tables that they might have memorized, they've still got a strategy that can deal with it. So they can look at this and go, well, I don't know what 20 times 18, but I could split my 20 into 10 and 10. And so they could go, well, 10 times 18 is 180, and then another 10 times 18 would be another 180. So if I double 180, I'm going to get to 360. So while the box method does have the potential to completely divulge into another just abstract representation that kids get lost in, if you go about it the right way and build up from concrete materials and from real experience in terms of showing that distributive property, it can be a really powerful tool and can definitely strengthen students' ability to think multiplicatively with numbers. But I don't know, what do you think?